Okay, so last time we talked about the concept of momentum, which involves the multiplication of a mass times its constant velocity. Mass times velocity is momentum, or you could say constant momentum because it's a constant speed. So P equals mv, the units are kilogram meters per second. And we know that an outside force is going to be responsible for changing the velocity of an object. So that's what we know in Newton's second law, that it's going to take an outside net force to accelerate the object from one speed to the other speed, to another speed. That initial speed could be 0 to some non-zero speed, or it can come from a non-zero speed all the way down to 0. So in either case, that is under the influence of an outside force. So momentum is kind of like an extension, if you will, to Newton's first law. One second. So it's kind of like another way of looking at an application of Newton's first law, where the net force in the system will be equal to 0. And when there is a net force, we change the object's velocity. Therefore, we will be changing the object's momentum as a result, because we know momentum is mv. And so when we have an outside force to cause an acceleration, we are going to change the object's momentum. And we also understand that in order to change the object's velocity, that is, change the object's momentum, it's going to take a certain amount of time to do so. There's a rate of change of things, a rate of change of position, giving velocity. Rate of change of velocity is an acceleration. So delta V over delta T is acceleration. So mass times acceleration is a change of momentum over change in time, which is a force. So in order to change an object's momentum, which takes time to do so, which is this first expression here on the left, that is, you're actually looking at another equation for force, for an outside net force, equals mass times delta V over delta T, which is acceleration. So this is another way of expressing Newton's second law. F net is mass times acceleration, or in terms of momentum, the outside force here changes the momentum in a certain amount of time. You can't change anything without a time interval, as with an appreciable time interval, that is one that is measurable. And then the next part here, we were trying to get an equation for delta P, the change in momentum. We multiply both sides by delta T, and we get rid of the delta T here. And then we just basically come up with an equation that verifies our intuition that delta P, change in momentum, is mass times delta V. Because P equals mv, then change in momentum, or change in P, is mass times delta V. These are vectors. You don't have to write the arrow, but it's all, things are written for a reason, to let you know, oh, okay, those are vectors, and my mass I know is a scalar. It doesn't have any direction, just a magnitude. And delta V is final minus initial. Delta anything is final minus initial. Delta X, X final minus X initial, delta V, V final minus V initial, and so on. And delta P, P final minus P initial. Okay, so so we're going from an initial velocity to some final velocity by way of a force in a certain amount of time. We then took a look at impulse. Impulse is the application of a force in a certain amount of time to change the object's momentum. Delta P over delta T is a force that changes the object's momentum, mass times acceleration here, delta V over delta T. So this is force, mass delta V over delta T. And we multiply both sides by delta t to get a change in momentum here, which is what we did up top to get this equation. So yeah, we did that up top to get our delta P mass times delta V. But here, yeah, so here we know that this is a net force. Force is a change in momentum of a change in time. And so if we were to just express this in terms of the momentum change, because a force changes its momentum. So in order to express that, we multiply both sides by delta T. We get rid of delta T here. And what we have here is F delta T equals M delta V. So F delta T is the equation for impulse. Impulse, which is force times delta T, is equal to a change in momentum. It takes some force coupled with time or multiplied by time to give me a change of momentum for that object. So that's my impulse I, and I wrote it down even further, you know, as we come to it. So that is impulse equation. Impulse is a change of momentum. I need a force acting over a certain time to change the magnitude and or direction of an object's velocity. And when I do that, I've changed its momentum. So this equation here, I equals F delta T equals M delta V, is the impulse momentum theorem equation. Very similar to the work energy equation, where we have work is equal to a change in kinetic energy. So impulse is equal to a change in momentum, very similar to what we developed with our work kinetic energy relationship. We were then talking about how, in reality, the impulse is force times time. We can put everything into a force time graph, and in reality, the force actually changes over time. But we're going to take a look at the force as an average force to keep things simple. But like I was giving an example of a baseball bat hitting a baseball. The first part of the contact, the initial contact, the force begins, and then like mid swing, it's maximized. And then at the end of the swing, the baseball loses contact. And so that impulse is now, you know, it's going to be zero at that point. The ball is going to fly off at a new velocity. It's going to more than likely fly off at a higher velocity than it came in. So this is the reality. The force starts from zero at some times, call it, you know, T initial here, and that's the final time. And so the force actually goes from zero to a maximum back to zero. But on average, we're just going to keep it, for our problems, we're just going to model it as a constant force, which we call an average force, which is what we see in the red. So again, anytime you have a multiplication, that is an area under any type of function. It's an integral. And anytime we have a division, that's going to be a slope. So here we have, you know, the area underneath this curve will give us the impulse. Whereas if we were going to divide force over time, that would be a slope. So all divisions are slopes, all multiplications are areas. So the area of this will be our impulse for this problem. So again, impulse, average force, delta T, which is change of momentum. And then we did some examples. Are we clear on the impulse relationship? Any questions on any parts thus far? Just a review from last time, a recap. Okay. If not, we will continue on. Okay, so we did the example, just a made up example, momentum question. So we had an object with mass 5 kilograms and it's moving along at 3 meters per second. And what is the momentum? 15 kilogram meters per second. Very easy. And then an impulse question. I think I had a baseball or some object with this mass, 0.5 kilograms, initially moving at 15 meters per second. And then it came to rest. I think it was a football, and a receiver caught it and brought the ball to rest. So the speed changed from a large value, non-zero value, 15 to 0. The catch, the force of the catch provided by the receiver changes the object's momentum from mass times initial velocity 15 to mass times 0. So it changed it from initial value of mass times velocity to nothing. And so the ball came to rest. And in order to do that, the impact, the force of the receiver, the ball caught by the receiver provided that force to stop it in about 0.02 seconds. And we also know that the force of the football onto the receiver is going to be equal and opposite the force of the receiver on the ball. AKA, it's the same as saying the impulse of the ball on the receiver is going to be equal and opposite the impulse of receiver on the ball. So because the force impulse is a function of the force. It depends on how much force. And we know that the forces are equal and opposite, therefore the impulses are equal and opposite, because this is a relationship here. So impulse of object 1 on 2, I'm just going to generalize it, is equal and opposite the second object on the first object. So again, this is an application of Newton's third law by way of impulse. So it all starts to relate. To start seeing the commonalities, relationships between impulse, Newton's third law, impulse, Newton's second law. Newton's second law is the application of an impulse to change an object's momentum, which is changing the object's velocity. And then momentum itself, P equals mv, is just Newton's first law, where the outside forces are equal to 0, and it's just cruising along at a constant speed. Obviously, there's no situation where you can look at realistically, if you have 0 momentum, yeah, that's, Newton's first law as well, but that doesn't do anything for us. So that's why we have that. So the impulse that we will calculate is the same in both directions, because the force is the same in both directions, just one is opposite the other. So we got our impulse equation, I equals m delta v, which is F delta t, but we don't have a force, and so it's counterproductive to try to use force times time, although we could find it if we wanted to. Let's keep our life simple. We also have this equation, m delta v, mass times the change in velocity, final speed is 0 minus 15, and we get negative 7.5 kilogram meters per second. And the impulse units are Newton seconds. So in this case, we could say negative 7.5 kilogram meters per second or negative 7.5 Newton seconds. Okay, so that's one problem. And then, okay, so let me go down here. We did this last time. All right, so basically where we are, so we're at the end of section 9.1, where we're talking about linear momentum and its conservation. We've done section 9.2. That's all impulse, and we sidestepped all the calculus. We don't really need to apply that here. And then we'll touch into section 9.3. So back to section 9.1, where we talk about the law of conservation of momentum. So I'll just apprise this here. So we were from last time, section 9.1. we've just been talking about how impulse is the change of momentum because it takes a force, coupled with time, force in time, to change magnitude and or direction of an object's velocity. So again, just repeating what we've been talking about just as the intro and what we were talking about last time. Just to write up the full equations, impulse is force delta t, which is changing the object's momentum, which is mass times change in velocity, which we know that delta v is v final minus v initial. So all of those things are equivalent. Those are all impulses. We don't change the velocity, that is the momentum of an object, without the application of an outside force. So again, let's consider a ball hitting a wall. So we have the ball coming in, certain mass, and going to the right. So that's going to be a positive velocity. And then there's an impact of the ball on wall and wall on ball. The force of impact here is going to be the impulse provided by the wall on the ball. And that impulse is going to be the force of the ball on ball times delta t. The ball is going to rebound. And so we have the same ball, and now that's the final case. So we have interaction of ball on wall, impact of the wall on the ball, and then it goes back the other direction. So that's our final case where the momentum is actually changing in magnitude, but definitely by direction. So the wall has provided an impulse. All right. Now let's say we have two balls that are moving towards each other. Okay, so we have this, let's say we have ball number one, let's call it mass one, and it has an initial velocity going to the right. And then we have ball two, and since it's going to the left, it's going to have a negative velocity initially. And so the thing is, what we're going to see is that just like with energy, the action that's going to take place between them, the impact is going to be the separation from what happens in the beginning from what happens at the end. So when they hit each other, so there's going to be an impulse provided by one onto the other. So the first mass is going to provide an impulse on the second mass just at the same time that the second mass is providing an impulse on the first mass. So what we essentially have is, this is the impact. And so we have two objects, two forces, they're equal and opposite. So we say the force of 1 on 2, or the impulse of object 1 on 2 is equal and opposite the impulse of object 2 on 1. Notice that the time there's no subscript on that because it happens in the same amount of time. So if we slash those times out, we'll get back Newton's third law that F1 on 2 is equal and opposite F2 on 1. We know that, okay, that's first principles, but we don't have to deal with that in developing our conservation of momentum. So this is the impulse of object 1 on 2. We also know that impulse is mass times delta V. So what we can then say is F1 on 2, or the impulse of object 1 on 2, is equal to M1 delta V1, which is equal and opposite M2 delta V2. And we know that those deltas are final minus initial. Okay. So after the impact, object 1 rebounds. It goes, let's say it goes back to the left, M1, and then we say negative V1 final. And then object number 2 rebounds the other way, M2 V2 final. So what I'm going to do now is I'm going to take this equation and develop a relationship between their momenta. And then we'll see what we can say at the end about that relationship. So the first side of this equation, we have M1 delta V1 is going to be V final 1 minus V1 initial. And that's going to be equal to negative M2 V2 final minus V2 initial, because that's their equal and opposite impulses. The impulse of 1 on 2 is equal to 2 on 1, and that's also equal to the F delta T is equal to M delta V1 equals the opposite of M2 delta V2. And this is the same equation stretched out in terms of their final and initial velocities. So simplifying that, so we have M1 V1 final, just switching the subscripts around. M1 V1 initial equals negative M2 V2 final, and then we add those. This here is going to be M2 V2 initial. So what can we do next? Just leave it this way, or is something else we can do? There is something we can do, but what do you think is next, the next step? What do you notice about the terms?
Should we put the initials on one side and the finals on the other?
Yep, group-like terms, exactly. So let's do that. I'm going to put the initials on my left. I can put them on the right, everything being positive. Okay, so then I'll have M1 V1 final, group this final term over here, M2 V2 final equals M1 V1 initial plus M2 V2 initial. So what we have here is an equation of conservation of momentum. So whatever the momentum is in the beginning, which is comprised of objects 1 and 2, is going to be the same momentum in the end. So we have, so this is going to be expression of final momentum equals initial momentum. And we know that momentum is mass times velocity. And in this case, this, you can treat this as, say, like a sum of all the momenta. It could be 2 or 10 objects on either side of the equation. And the sum total of all the momenta will not change. It will be the same from the beginning to the end. So this equation here is known as our conservation of momentum equation. Whatever the momentum was in the beginning will be the same in the end. They're equal. And we get to this point by looking at the impulse provided by both objects on the other. So that the equal and opposite impulses allow us to come up with this relationship. We just, we just wanted to simplify the matter. We want to carry everything through, and then we come to this final conclusion, which we denote as the conservation of linear momentum, because there's going to be another type of momentum later on down the line, talk about angular momentum, but that's when we get to rotational motion. So yeah, so that's what we have at this point. Any questions on any parts of the process? That seems pretty easy. Hopefully. So yeah, that's conservation of linear momentum. So let's see. That's basically the end of section 1. Another thing I wanted to say, let me see. So again, initial momentum equals final momentum. Much like for energy, when we have, the sum of all the changes in the energy for conservation of energy, that's equal to 0. The same thing goes for the sum of the changes in linear momentum. So basically, the momentum, the initial momentum and the final momentum, the sum of those changes is equal to 0. That's just another way of saying what we have up top, that the momentum doesn't change. Because if we had the sum of the changes equal something, then there is a change and there's no conservation of it. So that's something changing. In this case, we're saying that when you add the changes together, you don't get anything. That means it's constant. That means it's conserved. It doesn't change at all. And we re-express it simply in this form here. All right. Okay, so yeah, that's the end of 9.1. The 9.2 is the impulse. And so what we can do now is take a look at the beginnings of 9.3, and then let's see how many example questions we can go. I want to kind of go over some old example questions, so maybe we can go into breakout rooms for a couple of these momentum questions, a couple of old energy questions. I want to add on to some of those guys. But okay, so moving on to 9.3. Again, we'll be coming to this and more after the break. Collisions in one dimension. When it comes to momentum, there's two types of collisions. There's the elastic collisions where 2 or more objects hit and they rebound. It's like an elastic, it's just a bouncing off. And then there's another collision where it's called a perfectly inelastic collision, where 2 or more objects hit and they stick together and move as one unit. In both of those cases, the momentum is saved. But on only one of those cases is energy saved. So we're going to see the relationship between those two types of collisions, the conservation of momentum in those collisions, and whether or not energy is saved in those collisions. So let's consider the first case I mentioned, the elastic collisions. You know, basically, two or more objects, they hit together and rebound. There's an elastic, there's a bouncing off. That's the basic idea. We're going to find out that momentum and kinetic energy are saved. Because for the most part, in reality, when two or more objects hit, there's some energy lost in the deformation of those objects, temporary deformation. But since that deformation in the elastic collisions is really so small, we don't even worry about it. So for the most part, both quantities of momentum and kinetic energy are saved, because that little deformation that happens in the impact is, you know, very negligible. Okay. So that's the verbiage, that's the concept. So the equation that relates those two things. So let's say we have two objects. The equation is the same that we had up top. So the momentum in the beginning is going to be the momentum in the end for two or more objects. Okay, so that's basically, not only is that the equation for the conservation of momentum is the same on both sides, but it's also the equation for elastic collisions. In this case, it just involves two objects. And then we also will prove in certain problems that kinetic energy is saved. So the equation for that would be, you know, first mass and its initial velocity. And we have the second mass here. V1 final squared plus 1/2. So the kinetic energies on both sides are the same. And we'll be, let's take a look at a problem that involves the elastic collision case for the momentum equation. There's another type of collision, as I mentioned. Perfectly inelastic collisions. So two objects hit and stick together. Not elastics, inelastic, meaning that they're coupled, they stick together and move as one unit. So they're going to be moving with one common final velocity, even though that both objects could have had their own individual velocities in the beginning. So perfectly inelastic collisions. Let's see, momentum is saved. Kinetic energy. Well, let me just rephrase that. It's not completely lost. Yeah, some kinetic energy could be lost in the deformation of object, the screeching of the tires, heat, sound. So some of it gets lost to the environment in those types of collisions. So general equation for that, M1 V1 initial And say one of these objects could be at rest, so one of these terms is going to be equal to 0. But, you know, once they stick together, they're going to move on. They're going to move with one common velocity. And likewise for the kinetic energy equation that relates these two. 2v2i squared equals 1/2. Any questions that seem straightforward or any?
How's the momentum saved, like in an example?
Yes, we're going to get there. Yes, exactly. Good. So we have stipulated, obviously we have derived the conservation of momentum. So now let's prove that, at least quantitatively. Okay. So, so we have this bullet, mass 10 grams, is equal to 0.01 kilograms. So this 0.01, 10 gram bullet is fired into a stationary block of wood. Let's call him first object, he's second. The bullet embeds into the block. So that would be a perfectly inelastic collision because we have an embedding of two objects that are moving, they're coupled together, they're sticking together. The bullet embeds into the block. The speed of the bullet plus block combination immediately after the collision is 0.6 meters per second. So we have a situation that looks something like this. That they're together and they're moving with one speed. So this is our perfectly inelastic. So we have to, in reading the problem, reading comprehension matters, choose the correct relationship, the appropriate relationship. What was the original speed of the bullet? What was the original speed? So V final, 0.6 meters per second. What is this guy? Because we know this speed of the block, he's at rest. So we got that, got everything. So now we're trying to find out V1 initial, and then let's prove that the momentum is saved. Okay. All right. Because we always don't take anybody's word for granted. We can derive it mathematically. Now let's go test it. Let's go, you know, prove that it works. Very good. M1, M2, V final. So we have everything. This guy goes away. And V1 initial, which is the bullet. This is going to be divided by M1. Okay, and then, so mass one is, what's that? 0.010. And then V final was 0.6. Divide that by 0.010. So everything written out. So what do you get from that? So let's see, check it in the back and that. Got 300.6. Reasonable. Bullets, you know, they move very fast. 300 meters per second is roughly about 600 and something miles an hour, right? Everybody get that? Questions? No. Might not get that. Okay, so now let's see if the momentum is the same on both sides. We're going to prove that this is true. So the first mass, is it 0.10. And we got the initial speed at 300.6. And we have 5. And then obviously 0, so nothing there. 5 plus. Okay, so let's see if that works. And it might be off a little decimals, a little uncertainty, but for the most part, the number will be roughly the same. It comes down to sig figs at that point, but let's see if the number is roughly the same. 0.006. And we've proved it. No, so it's exactly the same. It's just sometimes this will become like 3.007, 3.006, but it's pretty much 3 on both sides. Yeah, so that's what we get. So if the wood didn't move after impact, means no change in momentum. No, there is a change in momentum because the wood actually did move. But if it didn't move, then there would be a change in momentum in the bullet. Something would change because there is a force that occurred. So either the bullet goes through the wood or it rebounds for some reason. But in either case, it's going to be a change because there was a force being applied on both objects. Yeah. So any other questions on that? See that works? Okay. I think I'll leave that. What I did want to go back to is chapter 5. I want to do number 7 from the homework and just take a look about that, and maybe I can have you guys go into a breakout and do some additional parts of that problem. So if you want to go back to chapter 8, number 7. Yeah. So I'm gonna change my screen. Yeah. Okay, so I want to talk, a couple of things about this. So we have this. We have these 2 masses. We have first mass 5 kilograms, and the other guys on the ground. 3 kilograms there. It says the object of mass 5 kilograms is released from rest using the isolated system model, or basically conservation of energy. Because when you have the system isolated from the environment, closed off, you're using conservation of energy. So it's the same thing. You guys know that. I hope so. If you didn't, that's what it's referring to. Using that model, determine the speed of the 3 kilogram mass just as the 5 kilogram object hits the ground. So what I was gonna say about the momentum and the energy is that we have to choose what's the beginning point and the ending point. The equal sign, I like to think of the action. That's the action that takes place. And then what happens after the action is the energy in the end, or in our case today, as we talked about, the momentum in the end. So we have an initial condition, action, final condition. So let's dissect that. So we have the mass on the ground, and we got this pulley. So this is our first mass of 5 kilograms. Let's see, the height, distance to the ground, 4 meters. Could draw this. Okay. Anyway, and then mass 2. So this is the stuff in the beginning, and then action or equal sign, and then we have situation where mass 2 is not going to be in the air. Let's see. And then mass 1, okay, we're gonna come all the way down. So mass 2 is hitting the ground, and it's traveled 4 meters. And so this is basically the end. So the action took place, the block is released from rest. And this guy is in the air, so, but he's moving at some final speed. This final velocity for mass 1 is going to be the same velocity for mass 2. They move as one. We know from force problems that they're going to have the same common acceleration, because if we were doing it if we solving this problem in terms of forces, we could solve for the tension, and then we could solve for the acceleration in the system, and then use kinematics to figure out the velocity, and that velocity is going to be the same for both. So the final velocity of mass 2 here that they're asking for is the final velocity for mass 1 as well. So that's going to help us in setting up our energy conservation relationship. So this is our 2 pictures. This is our initial picture. And this is the final. That's why it's very important to get in the habit of drawing things out. If you just can't see it, just see what you can piece out of it one at a time. Write what you know. Get a visual. Determine what's happening in the beginning. Determine what's happening in the end. Where is the action taking place? With all of those ingredients, not in any particular order, but this is a way of approaching this, then we can set up our energy relationship, and we can also set up our momentum relationship when we're doing the conservation of momentum problems, because the same principles apply for both conservation of anything. So we can start setting up our conservation energy problems like this. We can see, we know that the energy in the beginning is made up of kinetic and potential. Now we're going to see if it is in fact, that's the general equation, is in fact the energy in the beginning both or one, or, and then in the end, KE final plus PE final. Well, look at the initial picture. What kind of energy exists in the initial picture? Anybody?
Potential.
Yeah. Is there kinetic there?
Not yet.
No, there's no kinetic in the beginning. It's at rest, as the problems told us. It is released from rest. But before the release, it's all at rest. So in the beginning, we just have potential. So this potential is going to be equal to, what about in the final case? What kind of energy do we have both energies or one? What type? Because after it's released, this guy is going to be moving. What about this guy? Does he hit the ground at some speed or does he hit the ground at no speed?
Some speed.
Yeah, he's going to hit the ground at the same speed as this mass over here. So this speed V final is going to be the same as this V final, as I mentioned before. And there's also a distance that this mass 2 traveled. He traveled from 0 to 4 meters in the air. So not only does he have kinetic energy, but he has potential. And this guy over here just has kinetic energy. He doesn't have potential energy because he's on the ground in the final case. So the initial potential energy of the system is going to be equal to both kinetic and potential. And that kinetic energy is going to be made up of both masses. The final potential energy is going to be made up of just this guy here. He's the only guy in the air, but he has a speed. And this guy is not in the air. He's on the ground, but he has a speed, the same speed as mass 2. So let's put them all together. M1GHI equals, we have M1 V final square. So they're together, they're moving, they have a common speed. They both have kinetic energy in the end, plus mass 2 GH. And so we're trying to figure out, we're trying to find out what VF is. So after this, it just becomes algebra. So get our relationship right. So M1. So I'm going to isolate this guy. So I'm going to subtract the M2GH. Final, I guess, because that's coming from the end. Equals. All right, so I multiply both sides by 2. That's going to be equal to 1 the final squared. All right, so now just divide both sides by the masses. So I'm gonna factor out well, this H, the H on both sides is basically the same. So I'm just gonna do 2GH M1 minus M2. All right, I got this. Square root. Plug in the numbers. And we're going to get roughly 4.42 for the speed of the 3 kilogram block as it goes in the air, which is the same thing as the 5 kilogram block as it hits the bottom. Two times 9.8. Height is 4 for each is not. And times 2, there's a 5 minus 3 over 8. That's what we should have got for number 7A. Questions on that? Seems okay. So what you did. Any questions on where the beginning, the end? So that's the whole point. Is I want you to keep in mind where your starting point is. The equal sign is some action that takes place. Did it collide? Was it released? Did something hit? Some sort of action. And then we see what happens in the end. So that's going to be the initial, what kind of energy is in the initial state? What kind of energy is in the final state? And after that, we can solve for what we need. And then so let's go for part B. It says, find the maximum height to which the 3 kilogram object rises, right? And so we're looking at 3 kilograms. So he has some initial potential, and we want to see how much further, or what's his maximum height going to be, which we'll see is basically how much more distance does he rise, because we already know that he's at 4. So there's a couple of approaches here. We can take the beginning from where, from the ground to where he is now, which means that he has potential and kinetic because he's moving at 4.42. The 3 kilogram mass has got a height, which is at 4 meters in the air. So he has both energies. That turns out to be the more straightforward. Or this approach where we can say, okay, now I'm at part B, and I want to establish everything from the perspective of the 3 kilogram mass, which I can because I can choose anything to be 0. If I choose 0 at the point of where the 3 kilogram object is, I can then solve for its height. But I have to keep in mind that he's already at a height of 4, and add the height that I'm going to get here to his initial height, and we're going to see what that answer is. We're going to find out that he actually gets up to about 5 meters. Okay, so let me paint this picture here. So so the 3 kilogram mass, so 5, this, I'm taking this to be 0. I'm taking this perspective. I'm not even looking at the ground now because I've already taken the problem from the ground to this point, which is 4 meters, but now I'm reestablishing a 0 point. I'm saying that this is now going to be my 0 for part B. Well, that being the case, this down here doesn't matter, all right? At least in, the initial part of part B, that down here doesn't matter. And I want to see how, what the height of this mass is going to be from this perspective. So this now is my new ground, h equals 0. Well, I know he's got a speed at that point because I just solved for it. So he has an initial kinetic energy because he has a speed, 4.42, 1/2 mv squared. And now I want to figure out what his height is going to be from this perspective, which is going to be my final potential energy. So he's going to get somewhere up here, and he's going to have pure potential. Why do we know it's pure potential? Because it's a maximum height. At a maximum height, the speed is 0. Goes back to kinematics. So let's see. So KE initial equals PE final. So I go, it's in 1/2 MVI squared equals MGH final. This guys goes away. PI squared over 2G. I just divide both sides by G. It's VI squared over 2G. 4.2 squared over 19.6. That's 19.6 over 19.6, so that's 1 meter. And you might say, okay, well, he gets up to 1 meter. But keep in mind, though, he gets up to 1 meter from this point, but he's already in the air 4 meters. So 4 plus 1, 5. Questions? Does that jive with you? See how that works? Now, of course, we could have taken it from the ground, the perspective of the problem and say, all right, kinetic energy, oops. Or what I'm about to say is that we could have included the height that he is in the air. So because we have a choice. We can choose this to be 0, or we can choose this to be 0. We choose this to be 0 now. He's got both energies. And this will give you 5. But I'm just showing you that there's obviously more than one way to do it, and perspective matters. It is up to you, it is up to the physicist, up to the problem solver to establish where you're starting and where you're ending. So that goes for energy and momentum. Okay. Yeah, I think we're running down on the time here, but let's. I want to put you in the rooms to see if you could, do some extra things like. Okay, 1 second. Yeah, the correct answer is 5. It is 5, because do not lose perspective here. I think what's going on is like visuals are going to be very important, and unfortunately, in the class I can't show you but we'll do the best we can. Not use that as an excuse. We're warriors. He's already in the air 4 meters, and okay, so good. We know that realistically he's already there 4 meters. But I say, because I don't want to look at 4 meters now. I want to say that this is my 0 now. I can say anywhere is my 0. And if I say this is my 0, I'm going to calculate 1 meter, but I add 4 here. So just to keep it straightforward until you perhaps get to that point, I would choose this as the global perspective, if you will. Well, don't forget that, okay? The mass is still in motion, yes. And you're going to get 1 meter, but don't forget that he's already in the air 4 meters. You don't say he's 1 meter in the air, he's already traveled up 1 meter. You will be reporting, that would be inaccurate. So let me just say this. So you have 1/2 m, just talking about this guy. So v1 vi squared plus, this is where the 4 meters comes in, and then that will give you the global picture of 5 meters. Try that and see, just in the time that remains. Everyone, or you can see it, you can just chill out, but that'll give you 5 for H final, because H initial is 4. And solve for H final. All right, so you're looking for this, and that will be vi squared over 2g plus initial, because this GHI over G is just, G's cancel. You get 5 there? You try that out. Why don't you guys try that out and make sure you get H final is going to be 5. Yeah, that's all it is. Exactly. So it's 5. But don't say basically just because you feel it. Let's prove it. Go ahead, calculate it. You guys are the quietest ever. Okay. Okay, no worries. (4.42 squared over 19.6 plus 4, 1 plus 4 is 19.6. Like you said, Leo. So again, the proof that you can choose any place to be 0. I can choose here to be 0, but keep, just be careful. Yeah, you're gonna get 1, but don't report 1. He was already 4, so report that. Time left. Let's see. Real quick. Get the tension in the rope. 5 minutes, 4 minutes. Let's see if we can get it. All right. It's force. Okay. Free body diagrams. So now we start seeing that we can put a lot of things into our physics problems. We can put like this. We can solve energy to get the velocity. We could actually get an acceleration by way of the tension, and then we could get a velocity, the same velocity by using kinematics. We got velocity in this case using energy. We can't use energy to get tension because tension is a force. Force and energy are different. So, but you can find several things. You can apply several different concepts in any given problem. It's frictionless, so can't use that right now. Then after that, we can figure out how much time it takes for the system to start and finish moving because of kinematics. So once we have our acceleration, once we have our time, our final velocity, then we can figure out how much time it takes to complete the action. So if we were doing that, tension, same rope, same thing. So system moves that way, so there's an acceleration that way, so it goes from rest because there's a release. This will be, let's call him, he was M2. And, yeah, negative. T is positive because it's moving with the acceleration. It is. And then we can solve for the acceleration in the system. That moves as 1. The displacement is 1. Its heights are the same for both. The velocity is going to be the same for both. The time will be the same for both. So kinematics, energy, forces, at least in this guy. And you can do that for anything. Start getting creative. All right, so it's all in the y direction. So T M2A, T plus M1G. System of equations moves as 1. It's a system, isolated system. See, start appreciating the whole picture. And the only way, or the best way to do that, is with practice. You go and practice many problems. I get assigned a couple questions, go do 2 more. Just get after it, because this discipline requires your practice. Okay, so these guys go away. What do we got here? M2G plus M1G. Okay, and then G, M1 minus M2. Yes. Yes, not a race though. Let's see if that's the case. All right, so A is GM1. At least the acceleration. And then, but yeah, let's verify that. So 9.8, mass 1.5. So that's 2, and then this is 8, 19.6 over 8. So the acceleration in the system is a little bit more than 2. 2.45 meters per second squared. That's for the whole system. Just like we showed before with energy, that the velocity is for the whole system. Now we can get the tension in the string. Just use, grab top. T equals M2A plus M2G. M2 was 3 times 2.45 times plus 9.8. Times 3, 36.75. Right on top of that, Sin. That's the tension, that's the acceleration. We can find the time, we can do a number of things. All right, so that's it. Yeah, so I'll give you a couple questions on momentum. You guys take care. Have a great Thanksgiving break.